Okay, hello everybody. Today we have lecture 6. We keep on discussing chapter 3, normed and inner product spaces, orthonormal bases and projections. So what we have done last time? Last time we have discussed finite dimensional norm space, and we have realized that the situation there is totally the same as if we would work in RD. That is, the space is complete with any all norms are equivalent on a finite dimensional vector space. It is complete, and all closed balls of spheres are compact, and hence compactness in a finite dimensional norm space is just closedness and boundness. Now, of course, we are interested in the more advanced situation in the case of infinite dimensional norm space, or roughly speaking, in a general situation. So now we will discuss general situation, clarify the picture there. And the first result in this field is the following theorem. It is also known as Riess lemma. So let X be a norm space with this norm, and X0 be a closed subspace, so proper subspace, so not X itself. Then the statement is that for any epsilon positive, there exists an element X, epsilon in X, such that the norm of X epsilon is exactly 1. And the following holds. This means that the distance between this element X epsilon and the subspace X0 is not smaller than 1 minus epsilon. So in order to clarify this, I have made a picture. So now my X is R2 and X0 is a proper subspace. So then there is X epsilon in X such that the norm of X epsilon is 1. That is, this is an element which lies on a unit sphere, so somewhere here, such that the distance between this element and the subspace is not smaller than 1 minus epsilon. So on this picture, there are a lot of elements which lie on a unit sphere and whose distance to x0 is not smaller than 1 minus epsilon. Here in the statement, we have epsilon strictly positive, but of course, actually, we are interested in epsilon between 0 and 1, because if epsilon is bigger than 1, then this stuff is just negative, and then any x epsilon satisfies the condition that its distance to something is not is big or equal to 0, for example. One more important thing is what about epsilon equal to 0? So here on this picture we have this x0 which has distance exactly 1. Also one more x0. But here we speak about strictly positive epsilon. Why? So remark 315. So if X is a reflexive norm space, one can choose also epsilon equal to 0. In general, the statement of this theorem is not true for epsilon equal to 0. There are some counterexamples. So I refer to the book of Bogachev-Smolyanov, Real and Functional Analysis. So this is a counterexample. So please pay attention. So this is not true for epsilon equal to 0. And moreover, on this picture, what I used orthogonal projections, which exist in R2. But here we are in a norm space and nobody said us that there are any kind of orthogonal projection. Yeah, so there is even no notion of orthogonality in a norm space, which is not an inner product space. Okay, so we cannot.
Sorry.
Yes.
So that's why we need this property. Yes. So this is a
Yes.
property of almost perpendicularity.
Yes. So this is just my statement number 2, that this Riess lemma is a kind of substitute for the notion of orthogonal projection. Yes. We have no the true orthogonal projection. Moreover, if we are in the infinite dimensional setting, so pay attention, this is a norm space, not necessarily Banach space. So this space is not complete, probably, maybe not complete. So probably this guy does not exist in X. This is in one hand. On the other hand, Yeah, so x0, please pay attention, x0 is a closed subspace. This is also important. Okay, so let us go further. So one more statement in the remark. If we remove the requirement that x0 is closed, we cannot guarantee that there exists just an element outside this x0 whose distance to x0 is positive, strictly positive. Yeah, so here for a closed subspace x0, we state that there exists an element whose distance is strictly positive. Distance to the subspace x0. Yeah, so if we kill this requirement, it will not work. For example, so probably you can suggest an example. Or, okay, for example, we can consider as x continuous functions, and as x0 we can consider polynomials. Yeah, so then x0 is not dense because it's not closed because x0 bar, so the closure of x0 is x itself. Yes. So the distance between any element in x and x0 is 0. Is it clear with this example, counterexample? Please give me some feedback.
Yes, it is clear.
Okay. So we have stated the lemma. Let us now prove it. So fix some epsilon positive. Okay, let us make it from 0 to 1. Since x0 is a subset but is not equal to x, so there exists an element z which belongs to x but not to x0. So any element which does not belong to x0. Let delta be defined as infimum of norms z minus y, or so infimum over all y's in x0. So this is what is called actually distance between z and z x0 by definition of a distance between two sets. Okay, since our subset x0 it is a closed subspace, then x without x0, so its complement is open. Yes, so z is an element of an open set, and hence z belongs to this open set together with some neighborhood. And hence the distance between z and x0 is strictly positive.
This is exactly what breaks in the previous counterexample. Delta will be just 0.
Yes, 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 yes. Indeed. Okay, now what we do further, choose some epsilon 0, strictly positive, such that delta over delta plus epsilon 0 is bigger than 1 minus epsilon. Okay, what we do next? Choose y0 in x0 such that the distance between z and y0 is smaller than delta plus epsilon 0. Such y0 exists by definition of infimum. So nobody said that this infimum should be attained, that nobody said that there exists y such that the distance between z and y is exactly delta. But by definition of infimum, there should exist y0 such that for any arbitrary chosen strictly positive epsilon 0, this inequality is satisfied. So this is exactly the problem here. So such guy may not exist, but yeah, infimum may not be attained, but still we can approach it as close as we want. Okay, sorry. So further, let x epsilon be defined as follows. This is z minus y0 over the norm of z minus y0. So this is then the element from the unit sphere. That is, the norm of this guy is, of course, 1. And for any y from this space x0, what do we have? So norm x epsilon minus y. So I just calculate the norm. I insert this x epsilon. So this is 1 over this constant, norm z minus y0 times norm. And inside the norm we have z minus y0 minus norm z minus y0 times y. Norm is closed. Okay, what we do now? Now we make brackets and then plus here. And we notice that x0 is a vector space. Yeah, subspace of a vector space means that it is a subset and itself a vector space. And hence this guy, since y0 in x0 and y in x0, so this is their linear combination. This is an element which lives in x0. And hence, what do we have? We have here norm, so distance between z and some element in this set. Hence, this norm, so this distance, so let me use some other color. So this stuff is then bigger or equal to delta by definition of delta. We agree?
Yeah, because the delta is the infimum of
Yes.
over all such expressions.
Yes.
And this is one of them.
Yes. So then this all is bigger or equal than delta over, and what happens here? This guy is estimated like here. And it is in denominator, so I can use this. But this is bigger than 1 minus epsilon. And we have proved everything. This is exactly what we wanted. We have constructed x epsilon such that for any y from x0, the distance is bigger than, yeah, even bigger. Okay, are there any questions? Okay, seemingly no questions. Okay, so let us go further. So we have finished with this lemma. Now corollary from this lemma. So let X be an infinite dimensional norm space. Then there exists an infinite set, so a sequence of infinitely many different elements, such that the norm of all elements is exactly 1, and the distance between any two elements of the sequence is strictly bigger than 1/2 for all m and n different. And hence, as a consequence, all balls or spheres of positive radius are not compact in infinite dimensional normed space. Okay, so I hope that it is almost clear, but let us nevertheless write down something. So let x0, x1 be just any element of x such that its norm is 1. Otherwise, just normalize this element. Take x1, which is just the closure of a span of this element x1. Then by theorem, by theorem 314, so by the Ries lemma, there exists an element x2 in the complement of x1, so x without x1, such that this element is again has norm 2, so element from the unit sphere, and the distance between x2 and x1 is big or equal to 1/2. Okay, now take x2, which is a closure of a span x1 and x2. Again, by theorem 314, there exists x3, which belongs to the complement, x without x2, such that the norm of x3 is exactly 1. And the distance between x3 and x2 and the distance between x3 and x1, they all are bigger or equal than the distance between x3 and this space, x2, and we can choose it to be bigger or equal to 1/2. And then, etc. Since our space is infinite dimensional, we can construct a sequence using this approach. Okay. Are there any questions, remarks? I need some feedback.
It's very clear.
Okay. So may I go further?
Yes.
Okay. Remark, note, on each infinite dimensional Banach space, there exists another non-equivalent norm such that X with this new norm is again a Banach space. So again, a reference where you can see the approach, how to show it. But nevertheless, please pay attention. In finite dimensional situation, all norms are equivalent. In infinite dimensional situation, this is not the case. And even there are non-equivalent norms which give us which both give us a complete space. Okay. And moreover, yes, the balls and spheres are not compacts in infinite dimensional spaces. Okay. Yes. So first of all, are there any questions to this block of information? Okay, seemingly no. So let us go further, and now we focus on orthogonal projection. So we will work in inner product spaces, and we will discuss orthogonal systems, bases, and projection. So now we have not a norm, but a scalar inner product, and hence orthogonality. We know what is the orthogonality. So first we give some definitions, which hopefully are known for you, but as a repetition. So we are in an inner product space, not necessarily complete, and we have a norm generated by inner product. So a system of elements, of a family of vectors in this space is called an orthogonal system if all vectors from this family are pairwise orthogonal. So how big this index set is, we don't know. Probably uncountable, very, very fat, we don't know. But just a system which satisfies this condition that all its vectors are pairwise orthogonal. It is called orthogonal system. Now, a system is called orthonormal. Orthonormal if if it is an orthogonal system and the norms of all elements are 1. An orthonormal system is called an orthonormal basis in this space X if for each element X in X there exists an at most countable subsystem. So this is important. Of this family, of this system, and an at most countable set of scalars such that we can represent this X by this series. So sorry for my notation. So I have written at most countable, so finite or countable. That's why I have written this like not like k in natural numbers, but k in some set M, which is a subset of natural numbers, assuming that M either is something finite, like 1, 2, 3, up to n, or the whole set of natural numbers. So once again, an orthonormal system is called an orthonormal basis if any element of our space can be represented in this way. So decomposed using this family in a way that this decomposition has at most countable many summands. Yeah, and these summands are coefficients. And this decomposition, so it is not anymore a finite linear combination, but it's at most countable. That is, it is a series in principle. So the series should converge, otherwise it is nothing. So the series converges in X. That is, if we consider the sequence of partial sums of this series, this series converges to X in our space. So I have written like this, meaning that if my M is a finite set, then my sequence just stabilizes and becomes just a stationary sequence, starting from some point. Okay, so once again, last time we discussed that there is this algebraic basis, Hamil basis. This means that we can represent any element of a space by a finite linear combination of elements of this Hamil basis. This is something else, ONB, something else, because we allow also countable sums of countably many summands. Okay. A system of vectors in our space is called complete if its linear span is dense in X. That is, if we take the linear span and then its closure, we obtain the whole space X. Okay. Is everything clear with all the definitions?
Yes.
Okay. Remark, so every orthonormal basis is a complete orthonormal system. So every orthonormal basis is a complete orthonormal system. Yes, because every X
By
is
definition.
reachable. And this countably many, this exactly, well, okay, not exactly, but corresponds to the closure of linear span.
It's interesting how we cannot generalize the definition from linear algebra, yeah, where we say that if we have a system of linearly independent vectors and the number of the system, the size of the system is the same as the dimension of the space. And here it stops working because we have infinite dimensional system.
Yes, so let us, so to say, start from the how to say in the normal direction. That is, we don't have anything, and we start to learn what actually happens. So once again, we just consider this case, and there are some definitions. First of all, we don't know if such guy exists at all. This is an extra question. If it exists, how many vectors it has? if they are comparable with dimension or whatever, yes? So all these questions, they are just questions which should be answered. So at the moment, this is all what we have. And then we start to work it out.
Yeah, so it's a bit like with definition of convergence in metric spaces and with topological spaces. So we can also define in linear algebra a basis in a similar fashion, and this can be generalized better. Yeah. Each
Yeah,
element
but
can be
now you should,
expressed.
once again, you should distinguish between Hamel basis and basis in this sense, yeah?
Yes.
Yes, and I think I have not specified it in the slides, but if we have an infinite dimensional norm space, this is of course a special case of norm space, then the Hamel basis is uncountable.
Mhm.
Hamel basis. This means that if we want to represent any element of X as a finite linear combination of elements of basis, then we really need uncountably many elements. Okay, what happens here, we will discuss. We will learn it, hopefully. Okay. So once again, every orthonormal basis is a complete orthonormal system. The vectors of orthonormal systems are linearly independent. What does it mean? Since this here we can have very many elements, so uncountably many. What does it mean that the system is linear independent? This means that any non-empty finite subsystem is linear independent. Moreover, if we have an orthonormal system, then we can normalize all its elements and we obtain orthonormal system. Remark, so if we have an orthonormal basis, and if we have represented some fixed element of our space X by this series, then the coefficients Ck are called Fourier coefficients of this element X with respect to this orthonormal basis, and they are uniquely determined by this formula. This is so due to continuity of the inner product. So let me probably clarify it in more detail. So we have this. This means that X is the limit of partial sums. Ck, Ek, E lambda k. Hence, if we consider, so what is Ck by definition? So, okay, no, Ck, let us keep it. So we consider this. Since inner product is a continuous mapping, it was your home task to show it. This is the limit of such finite, so partial sums. So let me use here something else like J, for example. And then now we use orthogonality and orthonormality of the system. Then this is just nothing else but Ck, assuming that n is already big enough so that J is already included in this sum. Yeah, using orthogonality and orthonormality. Everything is clear, I hope.
Yes,
Yes,
and the
but
euro
it should
weight
be
is set
CJ.
for
It should be CJ. Yes,
yes.
since I have changed the index. Okay, we go further. Second statement, in the above setting, the Parseval equality is true. So this is the Parseval equality. This is, of course, just the infinite dimensional version of Pythagorean theorem. By the way, the classical Pythagorean theorem is true just by the properties of scalar product. So if X is orthogonal to Y, so what should be the Pythagorean theorem? So it should be like this, I assume. Yeah, so this is just a scalar product of x plus y. And then you use sesquilinearity and orthogonality, and you prove this identity. Okay, this is the home task. But now the parseval equality. So if we have an orthonormal basis and we have some x, which is just the limit of partial sums of this series, then this holds. And let me also clarify it. So what do we have? So in one direction, so let x be the limit of partial sums. So again, then norm x squared, this is just scalar product x and x, and this is then the limit using the continuity of scalar product, and here sum k from 1 till n ck e lambda k, and then the second sum, let us use j from 1 till n cj e lambda j. But again, using linearity, orthogonality, orthonormality of the system, this is limit n tends to infinity. We use linearity of sesquilinearity of scalar product and orthonormality of the system. So this is just the sum, k from 1 till n, ck absolute value squared, and then the norm of e lambda k squared, which is 1. So what do we have from here? So on the left-hand side, we have finite constants. On the right-hand side, we have this. Hence, we see that the series k from 1 till infinity, absolute values of ck squared, converges. Converges to this norm. That is, parseval inequality is parseval equality is true. On the other hand, so let we have a sequence of elements from our field. I recall that we consider field of real numbers or complex numbers. So let we have a sequence of scalars, ck, such that is the corresponding series converges. Then, and this is an exercise, so doing similar things as here. This sequence is a Cauchy sequence in X. So if X is complete, which it is not assumed here, but here we have only this situation. So if there is X, which is the limit of such sums, then this holds. But also vice versa. If the right-hand side is finite, then the corresponding family sequence is a Cauchy sequence. If occasionally this sequence converges in a complete space, any Cauchy sequence converges, then there exists an element X such that this holds. So if X is complete, this sequence converges to X, which is just the limit of this series, ck e lambda k. And this is element in X. Well, actually, this is just a formal notation which provides us the limit of such sequence. In the case if this sequence is a Cauchy sequence. Okay, was just a remark. So to show that this is a Cauchy sequence, it's a very simple exercise for you. So let us go further.
Excuse me.
Yes.
So I want to ask why is the summation of ck square converge?
No. So we have two things. So here we assume that x is the limit of such sequence. From this, we obtain that such series converges and this holds. Vice versa, if we have a sequence of constants, scalars, elements of our field, okay. If we have a sequence such that this holds, that is, so the right-hand side makes sense, then this is a Cauchy sequence in X. If occasionally this Cauchy sequence converges somewhere, if there is an element X, which is the limit of this Cauchy sequence, then we are exactly in this situation and the Parseval equality holds again. Have I answered the question or not?
Actually, I mean, in the first point, we have a result that the summation of ck square converge to the norm of x also square.
Yes.
So how can we conclude this conclusion? Does it comes from that x is the norm of x is a finite number, so it must converge.
Yes. So inner product space is a special case of norm space. What does mean norm space? This is so do I have, probably I have, oh, it will take a lot of time. Just look at the definition of norm. Probably it's, so probably I have to go very far away, of course. What is the definition of norm? So this is in a product, this is in a product. Oh God. Yeah, so this is the definition of norm. So we have a field, we have a vector space over this field. And what is the norm? This is a mapping from the whole X to these numbers. Yeah. So that is, this mapping is defined on the whole space X. And so norm of any element from this space is a number from here. So it should be finite, positive, non-negative and finite. Yeah.
Okay. Then thank you.
Yes. Okay.
And by the way, here in the second point, we also immediately have that the limit, this series of ck squared will be, so that x that we have in the end, its norm squared will be the sum of
Yes.
ck norm squared
Yes.
by continuity of the
Yes.
inner product.
Yes. Okay, good. So hopefully we have clarified all the points here and we can go further. Theorem, Bessel inequality. So we have an orthonormal system, not necessarily basis, but orthonormal system. Yeah, for example, in R2, we can take E1 and this will be an orthonormal system, but not orthonormal basis. Yeah, so be careful. So now we are in a more general situation. This is an orthonormal system in an EPS X. For each X, so the statement is that for each X in our space, the set of indices lambda such that scalar product X and E lambda is non-zero. So the set of such indices lambda is at most countable. And we have this inequality. So here we, of course, have this norm x squared. Here we have something like this, but be careful, this is not a basis, it's just an orthonormal system. So the statement is that on the left-hand side, we have a sum of at most countably many summands. The sum converges, and this is a majoranta. So the upper bound for this sum. Okay, so let us prove it. We prove this Bessel inequality. Sorry. For any finite subsystem E lambda 1, etc., E lambda n of this system E lambda, we have the following, that x minus sum k from 1 till n x E lambda k, a product with E lambda k, so this object is orthogonal to E lambda j for any j from 1 till n. So we have not yet introduced orthogonal projection. But if we would say that if we have a finite subspace of our space X spanned by these vectors, then this guy is orthogonal to this. That is, this guy is orthogonal projection of X to a finite, closed finite dimensional subspace spanned by these vectors. But we don't say these words now, we just say this. So indeed, we consider scalar product X minus the sum k from 1 till n x E lambda k times E lambda k. So scalar product with any E lambda j. We use the linearity of sesquilinearity of scalar product. So what is it? This is so x E lambda j minus sum k from 1 till n x E lambda k times E lambda k E lambda j. And now we use orthonormality of the system. So only one summand survives with k equal to j. And then, so probably let me just write it down. So this is x times E lambda j. And then all of this is just equal to 0. Okay, therefore, if we consider scalar product x and sum k from 1 till n x E lambda k E lambda k, this is just the same as, so we as so x is just this sum plus this stuff, but this stuff is orthogonal to all E lambda j's, so we can neglect it, and hence this is nothing else but k from 1 till n x E lambda k E lambda k scalar product with what stays here. Well, what stays here? It is the same. Scalar product x E lambda k E lambda k. So once again, what has happened here? So I have represented x as x minus this sum plus this sum. And then I use linearity of scalar product with respect to the first argument. And then x minus sum gives 0, and then only sum remains. Okay, it's clear?
Yes.
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 So, okay, good. Then after calculation of the scalar product, we have, again, using SSQ linearity of scalar product. So this is nothing else but this stuff. That is exactly what we want here, but at the moment we have it only in the finite case, finite dimensional case. Not yet even. So we just have written something. Moreover, what do we have additionally? So scalar inner product of x and this finite sum k from 1 till n, x e lambda k e lambda k. Now I use Cauchy-Bunyakovsky-Schwarz inequality, which we have discussed last time. So this is smaller or equal than norm of x times norm of this guy. Norm of this guy is just sum k from 1 till n, these things. Again, so finite dimensional Pythagorean theorem. This is what is written here. Okay, so left-hand side is just, it is written here, we have calculated it. And so this guy is smaller or equal by Cauchy-Bunyakovsky-Schwarz to this stuff. So what we have finally proved? We have finally proved Bessel inequality for this finite dimensional situation.
Yes, we can divide both sides by this square root.
Yes. So, and I put everything into square, yeah. Yeah, so I just put square everywhere. And then, so I have Bessel inequality in this special situation. Okay. So one more remark. So with n tending to infinity, we prove Bessel inequality for what's happening for each countable subsystem of our orthonormal system E lambda. Okay, so we have proved it for any countable subsystem. Yes, because in this inequality we can take any n. The right-hand side does not depend on n. Now we should say that for any x we have this statement, and hence due to this statement this form makes sense. That is, the left-hand side makes sense as a at most countable sum. Okay, for that we need to write a few more things, but first of all, once again, so we have shown this for any countable system, but from this we can conclude something. So may I go to the next slide to write down?
Yes.
Yeah, so due to this, for any countable subsystem, what we have, so in particular, for each natural number m, there exist at most so many m times norm of x squared, so many indices lambda with inequality that scalar product x and this E lambda, scalar product absolute value squared, bigger or equal to 1 over m. So why it is so? Because so on the left hand side we have at most countably many. Yeah, so let us think about this. Or probably I can copy it. So we are thinking about this stuff. So on the right hand side we have a fixed number. On the left hand side we have, well, now already countably many. And so each semantic which satisfies, so we cannot have more than we cannot have more than so many semantics which satisfy this inequality, because otherwise, yeah, something will go wrong with this inequality. Yeah, so the left hand side will be bigger than the right hand side. Otherwise, if this is not true. Agree?
Yes.
Okay. So what
So
is
this is similar to how we prove that like any convergent series can have with non-negative elements can have at least countably many non-zero elements.
Yes. So it's exactly this. So from this, there exist at most countably many lambdas from this set, also here from this set, index set, such that scalar product x and E lambda absolute value is non-zero. So once again, let me clarify things. So the set of all lambdas such that scalar product x and E lambda is not equal to 0. This is the same as the set of all lambdas such that absolute value of scalar product squared is bigger than 0. But this is nothing else but the unit over all m in natural numbers such that lambda in lambda, such lambdas in lambda that this absolute value of scalar product squared is bigger or equal to 1 over m. So what we have used just that the interval from 0 to infinity can be represented as this union of such sets. So this set is at most countable, yeah. So actually even finite, and we have a countable unit of finite sets. So this set is countable, or at most countable. Agree?
Yes, a very nice argument.
Okay, good. So now we have powerful tools. We have Bessel inequality. And we go next step. So lemma free 21. So let X be an inner product space, again, not necessarily complete. X0, a linear subspace of X at the moment, also not necessarily closed. And A is an element which is not from X0. The following two statements are equivalent for a vector B in X0. So first statement that A minus B is orthogonal to X0, that is, we have this identity. And the second statement is that the distance between A and B is just exactly this infimum. So the distance between A and B is exactly the distance between A and X0. That is, this infimum is attained at B. So once again, lemma does not say that such B exists. Lemma says that if there is B such that one of these statements is true, then the other statement is also true. This is a technical tool, but we need it. So yeah, so today we have many proofs, but still I think it's important. So let us prove from 1 follows 2. So let A minus B be orthogonal to X0, and let X be some element of X0. Then so distance A minus X squared. This is just norm A minus B plus B minus X squared. Then we use sesquilinearity of scalar product, and the norm is the norm is generated by the scalar product. So this is A minus B scalar product with A minus B plus two real parts of A minus B and B minus X plus a scalar product B minus X with itself. Okay, so what is it? So first summand is just the norm of A minus B squared. The last summand is just the norm of B minus X squared. And what about the intermediate summands? So this guy, by assumption 1, is orthogonal to X0, but this guy belongs to X0 because X0 is a subspace. And we have that B belongs to X0 and X by our assumptions belongs to X0. So this difference also belongs to X0. So the scalar product is then 0 by our assumption 1. Okay, so we have only these two summands, but since this is something non-negative, we have that all of this is bigger or equal to norm A minus B squared. That is the distance to any other element from this space is not smaller than the distance to B. So B is exactly infimum. Okay, now opposite direction. So 2 implies 1. So let B be an element of X0 such that distance between A and B is just distance between A and X0. Assumption. So доказательство от противного. Assumption. So there exists some other element X0 in X0 such that the scalar product A minus B and X0 is not equal to 0. So we assume that 2 holds, but we assume that 1 is not true. That is, there exists some X0 such that this identity is violated. So assume x0 has one norm. Otherwise, consider, so normalize it, x0 over norm of x0. Okay, then take the following vector, b tilde, which will be defined as follows. It's a scalar product a minus b and x0 times x0. So with this b tilde, what do we have? We have that a minus b can be represented as b tilde plus a minus b tilde. And we have the following. Scalar product a minus b tilde with x0 is just scalar product a minus b with x0 minus a minus b times x0, and then x0 times x0. So I have just inserted the definition of b tilde to this scalar product. So what do we have? So this is just 1 by our assumptions on x0, and then everything is just then 0. Hence, we see that a minus b tilde is orthogonal to x0, but by definition of b tilde is here. So this is a vector which is collinear to x0. So it's a scalar times x0. This is what I write down. B tilde is proportional to x0, collinear or parallel. So what does it mean? This means that a minus b is orthogonal. This means, this means that b tilde is orthogonal to this vector a minus b tilde. So this vector is orthogonal to x0, but b tilde is collinear to x0, hence this vector is orthogonal to this vector. Okay. Then we can use the Pythagorean theorem, exercise, your home task, to prove the Pythagorean theorem that the a minus b norm squared is just a norm b tilde squared plus a minus b tilde squared. Due to orthogonality, we use just the Pythagorean theorem. From this, it follows that the distance, so the norm a minus b tilde is strictly smaller than norm of a minus b. And additionally, b plus b tilde is of course element of x0. Since b was element of x0 by our assumptions, and b tilde is also an element of x0, because x0 is a subspace, linear subspace. Okay. So from this, it follows that the distance between a and x0 is strictly smaller than the distance between a and b. And this is a Widerspruch. I have again forgotten this word.
A contradiction.
Contradiction, thanks. Thanks.
So if we assume that this distance, minimal distance, is attained at b, but
But this
the
does not hold.
orthogonality does not hold,
Yes.
yeah, we are able to create a vector that has a smaller distance.
Yes.
This is a contradiction.
Yes.
With these proofs, it's often that like you can easily check each step, but then when you try to remember it after some time, it's pretty difficult because like those steps may feel a bit artificial, like
Yes, yes, these things are technical, but it is not supposed that you remember by heart the proofs. The proofs are needed to draw the picture. So we start from the blank white page. So we have made some definitions, so axioms, yeah, definitions, and then we try to clarify, so what is the picture finally? So what properties do we have? Which properties we do not have? What is the relation between different properties?
sure. I will always try to find some intuitive way to like to feel the proof. Well, maybe like what we've said is enough. Yeah. So if they are not orthogonal, we can somehow construct a vector that will be closer. And
Yes,
maybe from
yes,
this you
yes.
can like
This is a motivation further to introduce the orthogonal projection. So far, we don't have it in this abstract infinite dimensional setting, but we are going in this direction. Yes. Okay. Of course.
Excuse me.
Yes.
Here we apply the so-called Pythagorean theorem, equality. But why don't we apply it when we prove Bessel inequality?
Yes, but here we have only two summands. And in Bessel we have starting from the beginning, we have just an arbitrary system. We don't know how many elements there are, infinitely many probably, but probably even uncountably many. So we have clarified the situation.
and I think we did apply it
Yeah, we did
for
apply
when
it
we
somewhere
took
here for
when we
partial.
took this finite part.
Yes, yes, yes. So in finite part, yes. But actually we have proved it, roughly speaking, yeah? Here.
Yes.
Yes. Okay. Okay, thank you.
Mhm. Okay, good. So we go further. It's a technical lemma just to feel that in abstract setting, and not a complete space, and just a linear subspace, if there is a B such that one of two assumptions are satisfied, then the other assumption is also satisfied. So the existence of the closest element, closest to a element of x0, so the existence of such element is equivalent to the existence of something which plays the role of orthogonal projection in the future. But now just the element such that a minus b is orthogonal to the whole subspace x0. Okay. So now corollary. So let E1, etc., En be a finite orthonormal system in X. Let A be an element in X. Then the vector which looks like this does satisfy this assumption. This was assumption number 2. And hence, due to lemma, it does satisfy also this assumption. Uh, and exactly this assumption is easy to check. And we actually have done it by discussing all this story here. So totally similar calculations, yeah, are applied here. So in the case our x0 is just a linear span of finitely many vectors. In this case, this is a finite dimensional subspace of a inner product space, and hence it is the same as, and hence it is closed. Yeah, so it is the same as closed span. Yes, due to our results of previous lecture. All finite dimensional subspaces of norm spaces are closed. Okay, and then there is this guy such that this infimum is attained. So, and hence all this, both things are true for this for exactly this B. And so what does it mean? This means that in the case of finite dimensional subspace of an inner product space, we can guarantee the existence of orthogonal projection of A onto this space. Okay. Now, what should we do in a more general situation? So remarks, so once again, note in general, such vector B, which satisfies statement either 1 or 2, and hence both of them of this lemma, does not need to exist for a given vector A. So lemma just says that if there is such B that one of these statements is true, then the other statement is also true, but does not say any word about the existence of such B. So corollary means that in the finite dimensional situation, here is this B. So B does exist. But of course, it is much more interesting to deal with a more general situation, and in order to work it out, we go further. And we need the definition of orthogonal complement. So let X be, again, an inner product space, not necessarily complete. M be a subset of X. Then we consider the following set. So this is the set of all X's such that they are orthogonal to M. Yeah, so scalar product is 0 for when we consider a scalar product of X and any element of this set M. So this set M with this sign is called the orthogonal complement of M. Remark, so the following, so this guy defined in this way has the following properties. First property, this guy is a closed subspace of X. So here I have written, so to say, twice. I have written linear subspace. It's somehow like oil is oily because subspace already means that M is a subset of X, which itself is a vector space or linear space. But sorry for that. So just to emphasize that M is closed and linear space. So let us clarify it indeed. So we have a sequence of elements in this orthogonal complement, and let's assume that this sequence converges somewhere to some element X in X. Then scalar product X and Y, due to continuity of scalar product, is just limit of such scalar products, but they all are 0 because all Xn live here. Hence, we have shown that this X also lives in M in this orthogonal complement, and hence all limit points of sequences are included. So so this guy is a closed subset of X. Okay, everything is clear?
Yes.
Yes, we go further. So linearity. So let we have two elements in this orthogonal complement. This means that this holds for all y's in M. Take any scalars, then consider the scalar linear combination and use the linearity of scalar product with respect to the first argument. So this is equal to this, but here we know that this is 0 and this is 0 by our assumption. Hence, this guy also satisfies this condition and hence lives in the orthogonal complement. So this is a vector space, linear space. Okay. Moreover, intersection of M and its orthogonal complement is exactly one single element, the origin of our vector space, or zero vector of our vector space. Since this condition should be satisfied for all y's in M and all x's in M complement, orthogonal complement. So, yeah, so there is only one guy who lives in both spaces. A third assumption, a third property. So let L be the linear span of M. Then the orthogonal complement of M is the same as orthogonal complement of its linear span. Consequently, for the closed linear span of M, the following is also true. So the orthogonal complement of M is the same as orthogonal complement of its closed linear span. I guess it is clear, and I don't need to say any further words about that.
Yes, because L complement is closed.
Yeah, so this is so, and all the rest you can show up again using the bilinearity of scalar product and continuity of scalar product here. So let it be exercise for you. Okay, we go further. Theorem. So let X be an inner product space, X0 be a closed, now it is important, a closed subspace of X, then its orthogonal complement is, we know already that it is a closed subspace of X, but what is new information is that we have this X is just a direct sum of X0 and X0 orthogonal complement. These two objects, so these two subspaces are orthogonal to each other. In particular, for each X in X, there exists a unique element X0 in X0 such that X minus X0 is orthogonal to X0. And moreover, this holds. That is, this X0 is just the closest element to X from this subspace. And hence, since this guy exists, since this guy does exist for any closed subspace of X, then due to lemma, which was this lemma, yeah, so this lemma, due to this lemma, we have both this and this. Sorry. So this vector x0 is called the orthogonal projection of x onto x0 and will be denoted in this way. So once again, what is the achievement of this theorem? The statement is that in the case we have an inner product space, not necessarily complete. In the case we have a closed subspace, not necessarily finite dimensional. Then for any x of x, there exists the guy which is its orthogonal projection onto x0. That is the closest element, the closest to x element from x0. And so such that x minus x0 is orthogonal to this set. So we did several steps in order to provide the objects which are orthogonal projections. So now we have, when we proved the theorem, we achieved the goal that we can make orthogonal projections in inner product space, but not everywhere, but orthogonal projections onto closed subspaces of X. Okay, so let us try to prove it. We have time, perfect. So we know that this X0 orthogonal complement is a closed subspace. Of X. And we know that X0 is orthogonal to X0 complement by previous remark. So what we do now, we show that each X in the space big X is an element of this direct sum X0 plus X0 orthogonal complement. So how we do it? So again, let delta be the distance. Between X and subset X0. Then there exists a sequence Yn of elements of this subspace x0 such that the distance between x and y0 tends to delta when n tends to infinity. Again, this is by definition of infimum. We show that this sequence yn is a Cauchy sequence. In X. But yeah, in X and actually in X0, the Cauchy sequence. So let epsilon be strictly positive. Choose a number n, and a natural number, such that the distance between x minus yn squared is smaller than delta squared plus epsilon squared over 4 for any n bigger or equal to this big N. Then, for any n and m bigger or equal this big N, by parallelogram inequality, equality, by parallelogram equality. I don't remember what was the number of this. Probably it was proposition 3.8. So what do we have by this parallelogram equality? So norm yn minus ym, norm squared, is equal to 2 norms of x minus yn squared plus 2 norms of x minus yk squared minus 4 norms of x minus yn minus ym half squared. So let me copy it.
And we don't have yk, right? In the middle, yn.
Yeah, so I used k n and m. Yes. So let me have k here for any n and k, because I have a picture with k. So n and k. Yes, now everything is fine. And also k here. Yeah.
And in the last.
Yes. Sorry. Yeah, thanks. So we have this inequality. So let me clarify it with a picture, but I will copy it. So this is the picture. So this is just my one yn and yk and my x somewhere. So we draw a parallelogram. And then yn minus yk, this is one diagonal. And then what is the other diagonal? This one, how to construct it. So this point is x. This point is just the middle of this interval, roughly speaking. Not interval, but okay, middle of the segment. Everything is in vector space. So this point is just okay, the middle of this segment. Okay, and hence this diagonal is twice more than this stuff. Yeah, so this diagonal is twice more than just this vector. And this vector is written here. So this is one diagonal. This is another diagonal. This is twice, this is this two more. So this is another diagonal, this one. And then what we have here, we have our four sides. So we have this via this parallelogram inequality. But what do we have by our assumptions? We call that what do we have? Which assumptions do we have? We have this for any n natural numbers, and yes, and we have this. That's why. What do we have here? We have, so let me write down first. Oops.
Well, first two elements become smaller. And this is what we want.
Let me write down what I have, and then let us see how we get it. So this is the first two due to this yellow stuff. Yes. But we have 4 of them. Yeah, so this is due to these two things. What about this stuff? So this is an element. Let me take some color. So this guy is an element of x0. And hence the distance between x and this guy cannot be bigger than the distance between this and this subspace. So the whole stuff here without square, this is just bigger or equal to delta. And hence, this means that this guy is bigger or equal for delta squared. And then when we subtract it, we get that the left-hand side, this guy is smaller than minus 4 delta squared. Okay, agree?
Yes.
Yes.
So the conclusion is that this guy, yn, is a Cauchy sequence. Well, in X, but actually in X0. Wait a minute. So it's a Cauchy sequence in X, but all elements they live in X0. So since X0 is closed, this means that it contains all its limit points. Hence, this Cauchy sequence converges in X0. That is, there exists small x0 in this big X0 such that yn converges to X0. Hence, what do we have finally? So norm x minus yn, it converges to norm x minus x0 in one hand. On the other hand, this converges to delta, which was the infimum. Okay, let me to be shorter, this is the distance between x and x0. Yeah. Hence, we get that these two things are equal. And x minus x0 is orthogonal to this space x0 by lemma 3.21. But this is actually all what we wanted.
Can you please show a formulation for a moment?
Sorry?
Can you please show a formulation of the theorem for a
Yes,
moment?
good remark.
Mhm.
So we have an inner product space, not necessarily complete. We have a closed subspace Then what we have shown that such guy does exist, that this holds. And from this, we have also shown that x is this direct sum because each x can be represented as x
Yes.
is equal to x0 plus x minus x0. This is element from x0, and this is the element of x0 complement orthogonal.
Yes, exactly. This is more familiar way to say it, and this is exactly what does this direct sum of spaces mean.
Mhm.
Yeah, thank you.
Okay. Now I see that the time is over. And of course, we have not finished the topic. So you see how many slides I have. So I suggest we continue next week. I think it's not good to just run too fast and skip everything. So I suggest we continue next week with this topic, finish this topic quietly, and probably our course will be one lecture longer. Hopefully we all survive. This we decide closer to the end of the course. Okay, agree?
Okay,
Yes.
no problem.
Okay, so are there any questions concerning what we have discussed today?
I have several questions.
Yes.
First, for this theorem 3.25, it can also be used to prove the Bessel inequality, right?
No, it was not used. I just said that what we did before with this Bessel and all the stuff, this is a kind of the way in the direction to introduce the orthogonal projection.
Um,
So there are different things. So in one hand, we have when we have inner product space, we can make the orthogonal projection. After that, so independently of this, we have discussed the notion of orthogonal systems, orthogonal bases, and proved some properties like Bessel inequality. But we didn't say any word about the existence of such systems, bases or orthonormal systems. Yeah, now this theorem about the existence of orthogonal projection will allow us to prove that such systems, orthonormal systems or orthonormal bases, they do exist, at least in good spaces. Yeah, and then everything will be, so to say, all together.
and
So
also due
our
to this,
problem is that we thinking in analogy with Rn, so to say. So we feel like we have this all already. We have orthogonal projection, we have Pythagorean theorem, we have it. So it's like our background that we feel it, but this is not true. So actually, we have nothing. We have just a, as I said, empty page of paper. We introduce the vector structure. So we have a set. We introduce the vector structure on the set. We introduce, let's say, inner product. And now we play what we can do further. So we have, once again, we have X, we have vector structure, we have inner product. So what we can do? So we have realized that we can do orthogonal projection onto closed subspaces. We have introduced orthonormal systems, bases, discussed their properties in case they exist. Now, next step would be to prove that such things exist, and this will help us. Okay, so the logic is clear. What has happened? What is not yet happened?
uh, could you please go back to the slide of the Bessel inequality? I think I have some misunderstanding of it.
Yes. This is the last. So assuming that there exists such stuff, we have this statement. But so far we don't know if there are any guy of this kind.
Sorry, we don't know what.
Okay, we don't know the existence of orthonormal bases. I mean, I mean, of course, if we have an infinite dimensional inner product space X, we just take one vector E1, and then we can take another vector which is orthogonal to E1, and it will be E2, and then we can take another vector which is orthogonal to E1 and E2, and we get E3. So we can construct some orthonormal system. At most countable, yes. But what is interesting for us is to have orthonormal basis. Not just a system, but orthonormal basis. And this means that we should work with some system, orthonormal system, which is interesting for us as a candidate for being a basis. And this means that this orthonormal system, so we don't know a priori, so how big, how fat such orthonormal system should be, and which properties in general an abstract orthonormal system should have to be a basis. So that's the point.
By the way, if we have equality in Bessel inequality, then it will be a basis.
Yes, but this we will be this we will discuss at the next lecture, of course. Yes, so we are going to prove the things which are expected, so to say, which are natural to expect. Yes, but at the moment, since we have not proved them, we don't know if it is true or not. Yes, so we have only what we have. So we have inner product. We have this nice theorem about the existence of orthogonal projection. And we have some preparatory stuff. That is, we have some definitions about orthonormal systems, orthonormal bases, their properties, but yeah, if they exist at all, this should be. So our investigation should be continued to get the final point, so to finalize, to combine all we know.
I think I get the point. So it's not always that orthonormal system can be expanded to a orthonormal basis.
Yes.
Especially in uncountable cases.
Yes. Yes. Yes.
Thank you. And also I have a question about the. Could you please go to page 12?
Which page?
12.
12?
12? Yes.
So
Sorry.
this page, yes?
Yes.
Yes, so you see, I cannot go immediately, or at least I don't know how to go immediately. Probably this is possible, but I don't know how to do it. Yes.
Okay. I'm thinking about this corollary. So, for example, if we I want to think to construct a counterexample for it, and also I know this must be impossible, but I'm trying.
What
For
is
example,
the
if
aim
we
of your
consider,
efforts? So what was the reason why you want to construct a counterexample?
because I think all balls of positive radius are not compact. It feels a little strange because I think the compactness have some relation with the norm. So I'm thinking that
Let us say the following. So compactness is related to the topology. So when we say something like this, it is assumed that we consider topology which is generated by the norm. Yes, but of course, then when you have this set, you may play with topology and take another one, and then the set of compacts will change also, in principle. Yes, but nevertheless, now we are in the topology which is generated by the norm. And yes, if the set is infinite dimensional, just using this Riesz lemma, we have proved that such sequence exists. And hence, this means, what does it mean? Such sequence exists. What does it mean? It means that we have a subset of elements in a unit sphere which is not totally bounded. We cannot create an epsilon net for this sequence for epsilon smaller than 1/2. We cannot cover the sequence by finitely many balls of small radius, sufficiently small. Yeah. So this set is not totally bounded in X, and hence it cannot be relatively compact, and hence all spheres and balls, of radius 1, and hence using linearity, yeah, of all positive radius, they cannot be compact or relatively compact, yeah, because total boundness is violated.
Maybe it will be easier to imagine something like L2 small, where we have a sequence of vectors 1, 0, 0, 0, 1, 0, 0, and so on. And in this sequence, each element has a norm 1.
Yes.
But in this sequence, the distance between any two elements, different elements, is always bigger than 1. Well, it is 1, and we cannot
In
extract.
L2, in L2, I guess the distance is this one, but
Yeah, thank you.
it's a finite, strictly positive distance. It's enough.
Yeah, and this is a sequence where we cannot get any Cauchy or convergent subsequence.
Yes, this is.
That's why this set unit sphere cannot be compact in L2. And here we do like it's the similar fashion, but now it's a bit more general setting.
Yes.
Where we use this Riesz lemma.
Yes.
We cannot just directly show this.
But the idea is totally the same as in L2 or in LP. And we have discussed it, I guess, in L2, as far as I remember.
But in L2 there is a phenomenon that the first coordinate has the same weight with the nth coordinate. But if we decrease the weight, for example, we product with a scalar 1 over 2 power n, then
we can scale our sequence with this exact constants.
Because it's a linear space, so we can scale the.
Yes.
Okay. Thank you. Then no problem. Thank you.
Welcome. Some further questions, comments? Okay. So seemingly no more questions. Then we continue next week. I guess I have to stop it somewhere.